Fine, today I am going to explain k-nearest neighbors with practical demonstration. Let's start. So what is k-nearest neighbors? K-nearest neighbors is a supervised machine learning algorithm composed of a specified labeled dataset accommodating training sets x, y, and would like to represent the correlation between x and y. The objective of KNN is to find out a function s that maps the input x to output y, and hence for a new test point x, Sx can assertively deduce the equivalent output y. In KNN classification, a new test point is categorized by greater number of ports of its neighbors, with the test point being allocated to the category most available among its k-nearest neighbors. If k equal 1, the new test point is assigned to the category of its only nearest neighbor. Now, the fit of KNN classifier is mostly hinges on the distance metric employed to recognize the k-nearest neighbors of a test point. The most popular distance metrics used in KNN are the Euclidean distance, Manhattan distance, Minkowski distance, and Hamming distance. The most routinely employed one is the Euclidean distance. If point P1 with coordinates x1, y1 and point P2 with coordinates x2, y2, then the Euclidean distance between them is calculated by the formula d equal to 2 over x2 minus x1 whole square plus y2 minus y1 whole square. For a specified number of nearest neighbors k and a distance metric d, a KNN classifier executes 3 steps to classify an unidentified test point x. First, it explores throughout the whole dataset and calculates distance metric d between x and all the nearest neighbors adjoining to x. Then, it counts the number of data points for every category among those k nearest neighbors, and finally the unidentified test point x is allocated to the category with maximum nearest neighbors. Now let's explore this concept by an example. In this diagram, if you choose k equal 3, the test sample, which is green polygon, will be allocated to the category of blue circle, as among those 3 nearest neighbors, 2 are from the blue circle. On the other hand, if you choose k equal 5, then the test sample will be assigned to the category of yellow square, as among those 5 nearest neighbors, 3 are from the yellow square. Now, let's demonstrate k-nearest neighbors in Google Colab. We will define a KNN classifier to classify 3 types of flowers from the Irish dataset. Let's go there. First, we like to import pandas. We are importing pandas because it is the most popular Python library which is used for data manipulation and analysis. Import pandas as pd. So pd is the shortcut name for pandas. Next, we like to import numpy library because it helps us to represent our data as n-dimensional array quickly and efficiently. Import numpy as np. We also need to import matplotlib library to plot figures easily. Pyplot functions in matplotlib helps us to create and decorate figures. Import matplotlib.pyplot as plt. Google Colab is very helpful. Lastly, we have to import Seaborn, which is a data visualization library based on matplotlib in Python. Import Seaborn as SNS. So let's run this cell. Okay, so it's okay. Let's go to our new section. So we like to import dataset now. So let's look at our dataset. I keep dataset in desktop. So if you go desktop, so there is the dataset. So here we have this dataset, Irish dataset, as you can see here. So in this dataset we have 1, 2, 3, 4, 5 columns. So first 4 columns are the features, or also called independent variables. So sepal length, sepal width, petal length, petal width, and the last one is the level or class. So we have 3 types of flowers. Setosa. In total, we have 50 observations in this dataset. First 50 are Setosa, then next 50 are versicolors, and the last 50 are Virginica. So from these 4 features, sepal length, sepal width, petal length, petal width, we like to identify these 3 types of flowers: Setosa, versicolor, and Virginica. So let's load this dataset into Google Colab. So data equal pd, we like to use pandas library to import our dataset. Pd dot read csv function, we have to use read underscore csv, that is a csv dataset. So as you can see, the name of the dataset is Irish, IRIS. So we have to write down that name in the bracket. So iris.csv, that is our dataset. Now, as you can see in our dataset, we have features and dependent variable. So we have to separate them. So first 4 column are the features, and the last one is the dependent or class. So we like to assign the matrix of features for this first 4 columns, and then we have to also assign the level for these 3 types of flowers: Setosa, versicolor, and Virginica. So let's define the matrix of features and independent variable vector. So let's assign a variable x for features. So x equal data dot iloc. Iloc is to locate index, so we like to locate index for those features. And as you can see, there are 150 observation, and for this 150 observation we like to take all the rows for those features. So that's why in Python all rows indicated by colon indicates range. So we like to take the lower range to the upper range. I mean, we like to take all the rows, so there are 150 rows, and we like to take all columns for the features except the last column. So last column is the class or dependent variable. So last column in Python, the value for the last column is -1. So we have to start with the range colon. So and the last column is -1. So lower bound starts from 0. In Python, indexing starts from 0. So it will start from 0, and it will take all the column except the upper bound. So upper bound is -1, which is for the class. And we have located the index for our features, but what value we have in those indexes. So these 4 values: sepal length, sepal width, petal length, petal width, these values. So we like to locate those values for our features. So that's why you have to write .value values. Okay, so that is our independent variable. Now we like to also assign our dependent variable y. So y equal data dot iloc, and again we like to take all 50 observation for our class, and then for column we like to only take the last column. So that is the species column. Here you can see this column, so class column. So and the last column is assigned by -1 in Python, and dot values, those three types of flowers. Okay, so that is the assignment for importing our dataset. Now we'll actually import this dataset. Before that, we have to load that dataset in Google Colab. So let's load it. So go to File and upload it from our dataset folder. Irish. Just click on that. Okay, so it is uploaded. So let's look at that dataset here. So as you can see, it is showing first 10 observation of those 150 entries. In total, we have 150 observation. So we have first four column are the features: sepal length, sepal width, petal length, petal width, and last one is the class, I mean species or types of the flowers. So you can, if you can take 100 observation in this. Okay, then we have here 100 observation, and then we have another 50 observation after that in second phase. Okay, so you can see here 100 to 150 of 150 entries. Okay, so now let's look at our features, and let's print our features and see what we have in our features. print x. So just run it. Okay, you have to run it first. So run this one and then run print x. So as you can see, there are four features. So those features are here. So those features as two-dimensional array, numpy array. So we got the features. So how many observation we have? If you like to see that, so just write len x. So as you can see, there are 150 observation. Now let's look at y. Print y. As you can see, we have three types of flowers. First 50 are setosa. So this 50 are setosa. Then the next 50 is versicolor. So we have another 50 for versicolor. And then last 50 is the virginica. So we have three types of flowers. And if you want to check how many observation we have, so just write len y. So that is the how many in total observation we have. So you can see we in total we have 150 observation, and you can also see that from the data set we have 150 observation in total. Now you can see here the dependent variable or class y are not in numeric value, so they are given in categorical value in like a string, setosa, versicolor, and virginica. So we have to convert this categorical value to numerical value. For that conversion, we have to encode them with the numerical value. So let's convert those categorical value into the numerical value. So we'll have to encode the categorical dependent variable. So to encode that, so you have to go to the scikit-learn library. So from sklearn dot pre-processing module, pre-processing, that is a module in scikit-learn library. From here you have to import label encoder. Google Colab is very helpful. It can help us really quickly. Then after importing that label encoder class, what you have to do, you have to create an instance of label encoder. So lencode equal label encoder, just put the parenthesis here, Okay, so that is the instance of label encoder. Now we want to apply this label encoder to our y variable. So we have three types of flowers: Setosa, versicolor, and virginica. So we have to apply feed transform method for that. So by feed transform method, we can convert the categorical value in the numerical value and then replace those categorical value into a numerical value. So new y equal ln code dot feed transform old y. Now after that, we like to print our y. Okay, before that, let's run this cell. Okay, now let's look at our updated y. So print new y. As you can see, all those Setosa flowers are encoded by 0 and all those versicolor flowers are encoded by 1, and then finally all those virginica flowers are encoded by 2. And if you like to see the length, so it will be definitely 150. So just check it. So len y, so you will definitely get 150. Okay, so that is a 150. Now after that, we got our features, that is in x variable, and we also got our desired class or y variable, dependent variable vector. Now we like to split those x variable and y variable into training and test set. So to split, let's import a function that is called train test split from sklearn or scikit-learn library. From sklearn dot model underscore selection, dual color is very helpful. Model underscore selection, we like to import train test split function. Now this train test split function can create 4 variables from those features and dependent variable y. Those 4 variables are xtrain, xtest, ytrain, and ytest. So we can create those 4 variables by using this train test split function. So let's create those: xtrain, xtest, ytrain, ytest equal train test split. So that is the train test split function. Then put the parenthesis, and here we have to put some values. So the first one is the features x, and the second one is the dependent variable y, and the third one how much data we like to put in the test set. So test size equal, we like to put 20% data in the test set. So test size equal 0.2. that means we have 150 observation in total, and among those 150 observation, 20% will go to the test set. 20% means I think 30 observation will go to the test set. And now we like to set another value, that is random state. Random state equals any random value. We like to set it because we like to experiment here. That's why if we run this cell for multiple times, we like to get always same test and train data set randomly. So we like to get test and train data set always similar. So if we run this for multiple times, that's why we like to set that seed random state equal some numeric value. Random state equal, let's set it to 3. You can set it any number. So it means that if you run this cell for numerous time, you will always get the same uh, test and train and data set. Okay, so here is the spelling mistake, so you have to put it random state equal 3. There is m. Okay, so we successfully run this line. Next, we like to print those values. So we have four variable here. So x train, x test, y train, and y test. Let's check those variable. print x train. Let's see. Okay, so these are the features. So there are 80% features in the x train set. Okay, and let's see what is the length of this set. Len x train, yeah, it's 120 because there is 80% in the training set. Let's print x test. So print x test and see what is the result. So these are the x test value, and let's check how many observation we have in x test. Just write len x test. As you can see, we have 30 observation in x test. Now we like to print y train. print y train. Train, just run it. As you can see, these are the observation in y train, and let's check how many values we have in y train. Should be 120. So len y train. So we have 120 values in y train. Now we like to print y test. So print y test and just run it, and you can see these are the y test value. So let's see how many values we have in y test. So len y test, just run it, and as you can see, we have 30 observation in y test. So we have separated our data set in 4 variables: x train, then x test, y train, and then x test, then y train, and lastly y test. Now we like to define our k nearest neighbors classifiers. Suppose I am a layperson and I don't have any idea how I can implement k nearest neighbor classifiers. What we can do, we can go to Google and search for scikit-learn library. SCIKIT, scikit-learn, and just click on the first link. And then click on the API, and then just go for nearest neighbors. Just search for it. Let's go down. There are lots of things here. So neighbors, here is the nearest neighbors. So in this nearest neighbors section, just search for k neighbors classifiers. Here is the k neighbors classifier. You can see, just click on that, and then just copy this name from here, and then go to your Google Colab and just paste it. Now just write here from, and then scikit-learn sklearn.neighbors import k neighbors classifiers. This is our classifiers here. And now we like to create that classifier k neighbors classifiers, that is knn. Just keep the name knn equal k neighbors classifiers. Now we have to put some parameters here from our intuition lecture. As you have already learned that we have to put the number of nearest neighbors, how many nearest neighbors we want to choose, and then we have to also mention the distance metric, the metrics we are going to choose for the distance. So here you can see the k nearest neighbors classifiers and the n neighbors, so equal 5. So we like to put that, and we want to put metrics equal Minkowski. So let's put that. So n NERGSPORs equal 5 and metric equal Minkowski, Kowski, Minkowski. Now Minkowski metric has 2 power. If you put p equal 1, that will be counted as the Manhattan distance, and if you put power equal 2, that will be counted as the Euclidean distance. Now we like to take Euclidean distance for this experimentation, so we like to put p equal 2, power equal 2 for our Minkowski metric. So this is our KNN classifier. Just run this cell. Now we have defined our k neighbors classifiers. Next we like to train our k neighbors classifiers. So let's train it. So we can train our k neighbors classifier by knn.fit method. Let's write that knn.fit fit, and we have to put 2 parameters. Those are xtrain and ytrain. So we are training our classifier on the training set. So xtrain and those corresponding ytrain, and let's run this cell. So our classifier is trained. Now we like to predict the test results. So let's go there. So ypred, PRED, pred means prediction. So we like to predict the test results. So we have the x test. So as you can see, we have already defined those x test here, x test values, and for those x test we like to get the corresponding y prediction, and we already have y test for those x test, but we like to get the prediction results. So let's get the prediction results. So ypred equal knn dot predict method we like to apply predict x test, and we like to print our prediction. Let's print our prediction, print ypred, and let's run this cell. So these are the corresponding y prediction values, and we already have y test values, and these are the y prediction values. Now we like to compare our prediction values with the y test values. Now as you can see, our y prediction values are in horizontal order, so you can give, they are given in horizontally, and y test, if you look at the y test is also in horizontal axis. We like to convert y test and ypred into the vertical axis, and then we like to concatenate them together to get a better view, so that we can compare the predicted result with the test value, y test or true value or real value. The y test are the true values or real values, as you already know. So we like to convert our y-pred into horizontal form to the vertical form. So you can write y-p-r-e-d pred vertical equal y pred dot, we have to use the reshape function for that, reshape, and we like to reshape horizontal form to vertical form. As you can see, it has 30 column, so those are I mean the length, so that is the length. So length will become the column, will become the row. So in our new y pred vertical variable, so we have to put the len y pred as row, len y e pred, and then this y pred vertical will only have one column, so column equal 1, and we can print it. So write print y pred vertical. Okay, so these are the y prediction in vertical form. Now we also like to print the y test or y true value or y real value in vertical. Just copy these two lines and let's go to a new cell and run it. So y pred, so we like to print also y test or y true. You can write y true vertical, y true true. Here you can write y true dot reshape, true dot reshape, len y true. Actually length of y true and prediction always same, there are 30 observation there. So anyway, so you can write it y true, len y true y, then you can write here y true vertical, true vertical, then just run this cell. Okay, so y true is not defined, so it should be y test, right? So just write here y test. Okay, here it should be also y test, and this one also should be y test. Okay, so we have converted the y test into vertical form, so those are the two level, and we also converted y pred into vertical form, those are the predicted level. Now we like to concatenate them together, so we like to concatenate them in horizontal axis. So let's concatenate them. So we like to concatenate them, I mean horizontally. So true pred equal np dot concatenate. So it has two parameters, so y true vertical and y prediction vertical. First we like to print those true value, and then we like to print those predicted value. So we have to put them into a tuple. So y true vertical, then the second one is the y pred vertical, so those are in the tuple, and we like to concatenate them in horizontally. So axis, we have to put axis equal, here you can see axis equal 0, but we have to make axis equal 1, so that is for horizontal concatenation. So axis equal 1, and then let's print true pred variable, print true underscore pred. Let's run this cell. As you can see, the predicted true value, the first column is the true value and the second column is the predicted value, those are printed. Okay, so here you can see true and prediction same level, same level, same level, correctly predicted, correctly predicted, correctly predicted, correctly. So very good performance. Model is doing very fine. So correct prediction, but here you can see there is one incorrect prediction. The true level is 1, but the predicted level is 2. So model made this mistake. And then we have correct prediction, correct prediction, correct prediction, correct prediction, correct prediction. Good. So among those 30 observation, model made one mistake, so there is one incorrect prediction. So model is performing very well actually. So there is only one mistake so far. So we can delete this cell. Actually, we don't need this cell, and we can also delete this cell. Okay, very good. So now we like to plot our confusion metric. So by using the scikit-learn library, so let's print it. So from sklearn dot matrix module, so we have to go to the matrix module, and we like to import confusion matrix. Import confu. Okay, Google Colab is suggesting us, very helpful. So after that, we like to create confusion matrix, confusion mat. So just like to give that name, equal confusion matrix, confusion matrix. Okay, and we have to put two parameter here. So first one is the y test, and then the second one is the y pred. So y test is the real or true value, and y pred is the predicted value, you already know. So y test comma y pred. Now we can print our confusion matrix. Let's print it. Print confusion mat. As you can see, this is the very basic form of the confusion metric, but if we want, we can decorate this confusion matrix with Seaborn and Matplotlib library. We have already imported those libraries. Seaborn as SNS and Matplotlib.pyplot as PLT. So let's decorate our confusion matrix by using the Seaborn and pyplot functions. Okay, so Seaborns are imported as SNS. So we like to create a heat map by using the Seaborn library. So what is a heat map? You will like to ask that. So heat map is basically a two-dimensional graphical representation of data where actually individual values are represented as colors. Here you can see in confusion matrix we have many individual values, so we like to represent them as two-dimensional color maps. So that is what is called heat map. So, and we can call heat map from the Seaborn library. So sns.heat map, and we like to map this confusion matrix in color bar. So confusion mat, and we have to put another parameter here. You can see anode equal none here given, so we have to make anode equal 2, because in those color space we like to see those numbers. So 10, 0, 0, and 0, 9, 1, 0, 0, 10. This number we like to see in our confusion matrix. So anode, anode equal true. Just put that parameter true. True. Okay, and let's run it. As you can see, so we got the confusion matrix in a more decorative way. So 10 here you can see 0, 0, 0, 0, 9, 0, 1. Okay, so let's decorate this confusion metric a little bit more by the PLT function. So we can give some X level, we can give some Y level, and also we can write the title here. Okay, so let's use our Matplotlib PLT function. PLT pyplot plt dot you can give x level actually the predicted level. So plt dot x level predicted level. Now give the name of y level also, plt dot y level. Y level is the true level, so true level. Okay, we can make those capital letter. This is the predicted level and this is the true level. Now give a title, so plt dot title, title. So title is a confusion matrix, definitely. So confusion matrix. And also you can write, okay, so also you can write actually plt.show for better visualization. plt.show. Now you can see a very neat confusion matrix. Here you can see the diagonal values. Those are the actually real values. So here you can see we have 10 setosa. Setosa is encoded by 0. So there are 10 setosa and all in our test data set, and all those 10 setosa identified correctly. So there are 0 here. You can see level 1 has 0 and level 2 also has 0. So that means all 10 setosa flowers identified correctly. Now the next one is the versicolor, and because the level 1 is given for the versicolor, and there are 10 versicolor also, and among those 10 versicolor, 9 identified correctly and 1 misclassified as this is actually the virginica. So 1 misclassified as virginica, and then in the level 2 you can see there are 10 virginica and all those 10 virginica classified correctly. So only 1 versicolor misidentified as virginica. So that is the only one mistake model has made. This model is pretty effective. It's performing very well. So there is in total 30 observation in the test set, and there is only 1 mistake, as you can see from this confusion matrix. And we also see from the real and predicted plot here. So there is only 1 mistake here. So this is the its true level is 1 but identified as 2. So true level is versicolor but identified as virginica. So that is the only 1 mistake model has made. So after that we like to find the model classification accuracy. So I mean there are 30 observation, and among those 30 actually you have already seen that model only made 1 mistake, so it identified correctly 29 results. So what is the accuracy of the model? So if you like to see that, so you just copy this line from here and just paste it. So from sklearn.matrix we like to import, instead of confusion matrix, we like to import accuracy score function. Accuracy score, Google Colab is suggesting us. So after that we have to pass 2 parameter in this accuracy score, accuracy score. So those parameters are y test and y pred. So y test comma y pred. So let's run it. So as you can see, the model is almost 97% accurate. That means it identified 29 observation correctly among the 30 observations. So 29 by 30, it's almost like 97% accurate. This model is this k-nearest neighbor classifiers. Now if we like to evaluate our model on a new data, so we can also do that. So here in our Word file we have a new data, so let's evaluate our model with this data. So here you can see we have four features, 5, 3, 1.6 and 0.2, and the label is given as setosa flower. So let's classify this flower with these features and let's see whether the model can identify it correctly or not. So to identify that, let's write prediction equal knn dot predict. So this is the predict method we like to apply if we like to predict for new data. So we have to pass those features as two-dimensional array. So what are those features? So let's look at 5, 3, 1.6 and 0.2. 5, 3, 1.6, 0.2. You have to separate them by comma, and let's run it. Okay, we have to print our prediction. Just write print print prediction, and let's see. Okay, so model is returning us 0. So as you know, we have given the numeric value 0 for the setosa class at the beginning here. So if you can go there, okay, here you can see these first 50 zeros are for the setosa. So here you can see we have the first 50 setosa here. So there are 50 zero for the setosa. So model is pretty good. So model can identify our new data as the setosa because it is returning us 0, and from this word file you can say this is the setosa flower. So this is all for today. Hope it helps. See you in another tutorial. Until then, take care.